buffer equation. But you have peculiar transport proteins in the proximal, distal, and loop of Henle. You have these different transporters. Remember when you took 231, one of the functions of proteins on a membrane was a transport protein? And here, you have transport proteins, but they work in different ways. One type of them are called symporters, which means when you transport one substance, another substance will get transported in the same direction. So when you are going to reabsorb sodium, you're going to reabsorb glucose at the same time. So here, if you look at this, you have these symporter membranes. Both are reabsorbed into the peritubular capillaries or vasorecta. Sodium reabsorption and hydrogen ion secretion go the reverse way. These are antiporters. Antiporter means that when you reabsorb one, you secrete another. So sodium and hydrogen, as opposed to sodium and glucose, get, when you transport one, you're going to secrete the other. Here, they're both going together. We'll see this. So if you take a look at this, here's the renal tubule. So this might be, say, the proximal convoluted tubule. Here's the peritubular capillaries or vasorecta, and here's your fluid. Now, if you got sodium in here, sodium has the capability of going through the junctions between cells. That's called paracellular reabsorption. When it gets reabsorbed in there, it'll go directly into that blood and become that part of plasma.
Can you repeat that? Paracellular?
Yeah, it goes between cells in the proximal convoluted tubule. So these are the tubular cells. That's paracellular reabsorption. Transcellular reabsorption is where it goes through a cell. Now here's the problem with sodium. If it goes into this cell, sodium does not get pumped out of there for free. Once you take in sodium, if you want to get that back into blood, you have to pump that out of there, and there's a price to be paid for that. You got to use ATP to get that sodium out of there into blood. Once it gets out of the cell on the other side, it'll go in here for free, but you have to pump that out of there. So that's that with sodium. If you look at the control of electrolytes, the proximal convoluted tubule is going to be, the reabsorption is going to occur here. 80% of reabsorption is going to occur here, no matter what happens with hormones. It's not influenced by anything else. It's purely by concentrations. Nephron loop, that's the loop of Henle, is 15% reabsorption is going to occur here, and it's going to happen no matter what happens there. It's concentration dependent there. But the distal convoluted tubule is a little different. 5% of the reabsorption is going to occur here, but reabsorption in this convoluted tubule can be influenced by hormones. Important to recall this. We'll take a look at this in a second. So the nephron tubules regulate electrolyte concentration in blood via secretion. So here they are. These are all the important electrolytes: chloride, potassium, calcium, magnesium, and water. So here, if you have them flowing along in this filtrate that came out of the glomerulus, these tubules and the proximal convoluted tubule can take these through paracellularly between those cells, or they can diffuse through those cells, slower rate, and go into those peritubular capillaries, so you can get all those back for free. Don't have to pump those in there. Water can be reabsorbed here as well, and water can be reabsorbed by osmosis depending on concentration. So that's electrolytes in the proximal convoluted tubule. So here's our symporter. If you have glucose in the filtrate coming out of the glomerulus, and you have sodium there, you have those special symporters, here they are, where glucose and sodium will come in here. Once you get glucose in there, that can move through that cell through special shuttles for free, and you'll reabsorb your glucose. However, when you get the sodium in there, just like we featured it before, to get that into blood, you got to kick in a little ATP, and now you can get the sodium in there. So that's how you use a symporter in the proximal convoluted tubule. So here, we look at the ascending limb. You have sodium, potassium, and chloride symporters at the apex. You have sodium is actively transported into the interstitial fluid. Active transport just means that you have to use ATP to do it. Chloride is going to diffuse into the interstitial fluid paracellularly. And then there's no leakage channels for potassium on the base of tubular cells, so potassium is going to move into that tubular fluid for free. Magnesium, calcium, sodium, potassium diffuse paracellularly. We just looked at that in that previous slide. That's between those cells, and it's not permeable to water, the ascending limb. The descending limb is primarily permeable to water and urea, but not most ions. So here you have one side that you can get most of those ions back. The other side, you can get water back and urea. All right, so here's your distal convoluted tubule and the symporter for reabsorption. Here's sodium, chloride, and potassium coming straight in here, same direction. Sodium, we said, if you're going to get that back into blood, you got to kick in a little ATP. Chloride is going to diffuse through a shuttle, you get that for free. And then all of these, sodium, potassium, calcium, and magnesium, can go paracellularly. So it's only the transcellular ones that they're going to have to go through that symporter. And then here's potassium. Potassium can go back out in channels, this through special channels, so this is concentration dependent. Okay, so that's what's going on there. This is to show you the loop of Henle, where you get active transport of sodium and chloride ions. So here you're going to be salvaging those, and then on the ascending limb, you're going to get rid of water. You're going to have water secreted. This is the concentration gradient that you have in the kidney. Out in the cortex, it's 300 milliosmoles. Does anybody remember what the concentration for normal plasma osmolality was? 285 to 300. So here, it's right on the cusp here. So when you get blood going into the glomerulus, now it's like, okay, so what's going to happen? And you pump it down that loop of Henle, and now look at the concentration gradient it's going. Down in the deepest regions in the medulla, it's 1,200 milliosmoles. That's 4 times the concentration. So when you get this coming down here, and now it's permeable to water, it's going to suck out that water, right? Because it's going through a concentration